Yeah, so so this is an interesting example of Sudoku. So I mean, we all solve Sudokus. So now imagine this input is given. These are not typed thing that is given to you, but these are handwritten digits. Okay, so now you're given a Sudoku table where these things are handwritten digits, so you have to recognize them correctly and then solve it. So you can do similarly. So the neural network, so you have a neural network and there will be basically, there may be one image, but this image has 81 different attributes. For each of them, so that's where before we had just one, because one digit had only with one attribute we're looking for. But here it has 81 different attributes, and each of them can take a value between 1 to 9, right? Yeah. And so that is expressed as this, so image, and then that's expressed as a atom, neural NN atom, like this. And then you have the standard logical rules. First, here saying that if you have identified a particular item as already 9, so this is where, I mean, there are blanks here, and then some places you have identified something, like the perception layer. Then you just assign, saying that row column the value is n. And for all the other ones, you pick one of the values from 1 to n. Okay, so this is like enumerating. And then, of course, that's not correct. Means we have to satisfy the Sudoku constraints, and these are constraints saying that in any row a number cannot be repeated. This is any column a number cannot be repeated. Any row a number cannot be repeated, and in any of these blocks, this is another rule, the number cannot be repeated. I got a little bit confused. I'm not clear. Is this what this symbol is and what this symbol is? So Jun, can you tell what this I is, right slash and left slash is?
Oh yeah. So because still I'm using Klingo as the engine. So I'm actually using Klingo symbols. Here the slash is actually division, but I only keep the integer part. I is the index from 1 to 81. That means that if I divided by 9 will give me the row index.
Oh, okay.
And I \9 will give me the column index.
Oh, okay. So suppose I have say 11. So what will be this number? So 11 by 9.
It will be 1 and 2.
Okay. Oh, sorry. Okay. So that's a clever term. So 11 by 9 is 1, and 11 this 9 is 2. Okay. So people can follow it. So that's basically it. In here is that you have this, you feed it to again, you can feed it to a CNN, and out of this CNN you will get, so you will get how many probabilities? 810 probabilities, right? Or no,
right. Actually is 81 times 10, so it's 810.
10 probabilities. And after that you have these rules. So, and 810 different is it 810 different answer sets? No, 810 probabilities means there's a lot of answers. So
right.
Yeah, how many answer sets are there? Is going to be there?
It's a really big number.
It's it depends on, of course, this how many of this you already recognize. But even if you recognize, you have probabilities associated with that, right?
Right.
You have assigned it. Okay. So exercise for you guys to figure it out. So, but I mean, I'm surprised actually this big thing works in you are able to run it. And so these are the data. So you're saying that with 25 training data, you are able to, so how big is what your training test? Can you say a little bit more about it?
Oh, yeah. So here's one thing. So although we don't train end-to-end in this example, we just show that we can solve this problem by separating the problem into perception and reasoning part. And in the perception part, we directly train the neural network to identify the given digits and empty cells. And then with that neural network, although the neural network make many mistakes, but by adding the constraints, we find the most probable prediction that satisfy all the constraints. And that thing can be done really quickly because Klingo engine can find the optimal stable model really quickly.
So what you are saying is, so you have a neural network mod. So suppose in the so in the training stage, what is your input and output, or how are you training?
In the training stage, the input and output are the actually input and output of the neural network. So the input is a single image, and output is the label of each cell.
Level. So input is output is kind of, so input and
roughly
so
like
input
this.
is like what you had, that thing, and output is basically the numbers, the 81 numbers.
Yep, right.
Okay. So input is Sudoku image, and output is 81 numbers. Not probability, just the numbers. And through this, you are training the convolutional neural network, right?
Right, to recognize the digits.
Okay. And so are you saying that just 25 data training is good enough?
Yeah, that's because the image itself is not handwritten in this example.
Okay.
So it's an easy task. But the problem is
I think this particular table is probably not very meaningful in the sense in these other cases. So here you are actually giving the ASP rules, and in other cases they are basically learning about Sudoku rules, right?
Right.
Input is text. So this probably this table can be skipped. It's not there.
That's just a use. And the first example, we want to demonstrate the use of separation of perception and reasoning. While that doesn't demonstrate the learning.
No, so what about this one?
This is similar. So the mistakes in the perception part can be modified or corrected by the reasoning.
Okay.
So
this happens during the inference phase or during
during the inference phase.
Yeah. So suppose in the inference phase you found a mistake. So what are you going to do?
We will find the stable model. So every stable model will not make mistake, right? So we'll find the stable model that has the highest chance.
Okay. So let's go slowly this one. So you are input a Sudoku table, Sudoku
image,
right? And so it went through the neural network and you got this value, and basically you are not able to solve it, and that's when you realize that you made a mistake, right?
Right.
So you're not able to solve it, you made a mistake. So what are you going to do now?
Because it's a choice rule. So the good thing of ASP that we don't just say that at that place we have a 7. We say there's a chance to have a 7, and we assign a probability to that chance, and in the end we will find if one interpretation doesn't satisfy constraints, although that interpretation may receive the highest probability or highest
chance. So you go down the second one, third one, like that.
Right. We just go down to the second one.
Okay, got it. So so a Sudoku image. So here, the AP, yeah.
So so when you're actually using the thing, as you generate those interpretations, so I'm not talking about training, I'm talking about the reasoning step. Do you have to generate all interpretations when you do reasoning? And if you don't, and as you go through that list, are you able to go to the next highest interpretation in an efficient way?
That's a good question. So So the reasoning part is actually done kind of out of the box. It's done by the reason solver called Klingo, and Klingo actually supports to find the stable model that has the highest chance. And so with Klingo solver, we actually don't have to really consider all possibilities. It has a very efficient implementation inside to quickly prune out all interpretations that has less chance.
Okay, and so that's pretty interesting. And so when you have to go to the next highest interpretation, you still have that efficiency, correct?
Right. Yeah. So like this is an extreme example. So in this example, the number of interpretations. So if we don't have constraints, then it's 10 to the power of 81 because there are 81 cells. Each cell has 10 probabilities. So it's a really big number. Also, if we add the constraints, it's still a very big number. But in the end, with Klingo, it can find the most probable stable model. I think it should be within a second. They point something to a second. So it's really fast.
A question from the audience, then I'll get you one.
So when it comes to Klingo and the connection there, when does that connection happen? Is Klingo the reasoner that happens after the neural network? So the output of the network is fed into Klingo set of rules that then make your decisions, or where does the Klingo come into play exactly?
Good question. So basically, NeurASP is a package, and in the package, we take neural network as one component, take Klingo as another component, and the Klingo just does one thing to find the most probable stable model. And to make that happen, in the paper, we have actually turned the probabilities into the so-called weak constraints in Klingo. So yeah, so Klingo actually, we just take it as a tool to help us to find the most probable stable model. And all the other computations are done in other Python modules.
Okay, that makes sense. Thank you.
One more question.
Is there a comparison between like the method you use with Klingo and usual neural networks? Is there a time comparison that how long does it take to solve the Sudoku?
So first, to solve Sudoku, my experience that using Klingo to solve Sudoku is much faster. I remember, but yes, if you use a backtracking algorithm to write it down, a backtracking algorithm to solve Sudoku, it may be also fast, but I doubt it would be as fast as Klingo. The good thing about other Python programs is that probably it allows for parallel computation, like utilizing GPUs with matrix multiplications. That's something that Klingo cannot do. So in terms of neural network training, typical neural network training packages would be faster compared to Klingo computing. So that is one of the drawback and limitation of NeurASP.
Thank you.
So June will be there for only 9 more minutes. So he has a meeting at 4. So let me go over the slides where I need his help. Okay. Let me see. Yeah, can you say a little bit quickly about this slide?
Oh yeah, this is the demonstrate the user table to show how it helps. The constraints helps when the perception part has mistakes. So we can in the first column the first column is the number of training data to train the perception neural network. Second column is the perception accuracy, and we can see that with for example 15% perception accuracy, the NeurASP in the last column can achieve 71% accuracy, and that is because although the neural network makes some mistakes, but we can prune it out for those mistakes. So and find the most probable answer to that solution. So that helps us to improve the overall accuracy of the solution we found by using the Klingo or using NeurASP.
This slide I can explain. Yeah. So can you, I mean, this weak supervision word is used differently by different people. So what is your notion of weak supervision, or what do you mean by saying this allows one to train under weak supervision?
Okay, cool. So typically in neural network training, one would consider the input and output of neural network. For example, for digit classification, one would assume something is given, which is that we have the image and we have the label. So that's called supervision. Weak supervision is the time when we don't have exactly a label, but we have some information about the label. For example, in the add 2 × 2 example, the input are 4 images in 2 × 2 grid. And the labels are not 7452, but rather the labels are the sum of them. Like the labels would tell us.
Yeah. So you are able to create more problems. And what is the advantage, or what is the goal here?
The goal here is using, although these are just toy examples, but we are trying to demonstrate that even if we don't have the label for something, we can still train the neural network using the weak supervision. So using the information about the label. If we know the relationship between the label, the label of the image, and the label we get in hand.
So here, what is your goal? To learn the digits or to learn this minus plus multiplication?
Yeah, there are two. These are 2 data sets. The first, in the first data set, our goal is to learn how the digit classifier.
Okay.
And the second, our goal is to learn the classifier for the operators.
Okay. So are you saying basically is that, say our goal is to learn these digits, and instead of just using the simple digits and the labels, we can combine this and create lots of data like this and train with it and be able to develop a better perception model? Is that the goal?
Right.
That's what you mean by weak supervision. Okay.
Right.
Okay, that's there. Okay, explain this one. 5 minutes. Okay.
Okay. So here is still it's still an inference example. Basically, we use neural network to identify some person and cars, and the neural network won't have the context information like a person should always be smaller than a car, typically, right? So with that information, we can and also with some other knowledge, like if an object is closer to the photographer and the bounding box is smaller, then for sure this object is smaller. So with this information, we can do some context relational classification about objects. Like in the first image, we can classify the 2 cars as toy cars. So that, yeah, there might be some other applications, but in this example, we just show this simple use case.
I mean, in this case, the cars are closer to the viewer and yet smaller. So definitely they're smaller than the person. So they're toy cars. Here, the cars are farther. So even though they are smaller, we cannot conclude they are toy cars. So we, by default, probably we conclude they're regular cars or something.
Right.
Okay. Yeah, the semantic regularizer, I think I didn't understand this once. You can say these 2 slides, so they're not relevant that much.
Yeah. So maybe
do you want me to slide, or yeah?
Do you want me to explain something about here?
Yeah. Good.
Okay. So basically, semantic regularizer is that during training, normally people would just use the data, input and output data for the training. But we are thinking maybe knowledge can also help us to give some signals to help training. For example, one example in the so-called semantic loss paper is the shortest path example. Well, the goal is to find a shortest path between the 2 red nodes in the grid. Well, the blue box means that edge is removed. So to make the problem more complicated. And we can see that if the model is trained purely from using the cross entropy loss, actually it will, the final prediction may not even form a valid path. But if we use the constraints, so use the gradients computed using with the constraints, then the output will always form a valid path. So it's possible not the shortest one, but at least is a valid path. That's the thing we want to demonstrate in this example.
Okay, good. Got it. I got it. Because you have the constraints, at least you get a valid path, because other non-valid parts will be thrown out. While if you use standard neural networks, I mean, you can train with as many valid paths, but there's no guarantee that it will find you a valid path.
Right.